So let's start. So at this point, you should have this notebook for WebbPSF is in reference, and the webinar. So I just save a copy to the home folder where the notebook is located. So in this case, you can do a PWD just to see where you are. This is the home folder where you're likely gonna have where you're running your notebook at this point. And this is the index. Once you have this, if you download the notebook to yourself, you can click on this and it's going to take you to each of the sections that you have here. And you have the links to the documentation as well. The first thing we want to do is to just download the tar file and extract that file. It's going to do that in that home folder. And then once that's done, we're going to set up that home folder to be our WebbPSF path. In particular to this WebbPSF data, which is the folder that is going to be on tar from that zip file. So if you do that, you set up your environment to WebbPSF path, and the way you know it's gonna, if it's working, is running the first cell that it should give you no errors, and it's just doing a setup of a first set of observations. This is basically everything that we need to do to set up this notebook. If you can run this cell successfully, that means that you should be able to run everything else that's coming from the notebook successfully. Make sure to save a copy of the notebook into your home folder. Remember that either as Collins did, if you go to reference, JWebbinar, and you go to the JWebbinar 34, so we are in JWebbinar prep, and you go to 34, there are a bunch of files here, but you should see the notebook that we're going to be using, and then you can copy the notebook and then just paste it on your sort of like home folder, and you should have a copy here. And if you do that, then your setup should work fine, because it is your home folder plus the WebbPSF data, which is the folder that is going to be created once you extract the tar file. And that tar file is going to be downloaded into the home folder. All right. So if you were able to run this cell, that means that you have everything set up correctly. And what we're going to be doing here is just starting with a very simple simulation of a PSF for James Webb. We can select our detector, we can select our filter, we select our instrument, and we can select positions. And now this is interesting and relevant because imagine that you have a particular set of an image, an observation where you're trying to subtract the PSF for a large group of stars. So you could see that, for instance, you can have a list of detector positions. So this will be a good way for you to set up a simulation where you just iterate over a list of your extracted positions from a particular image. And that may be relevant for you for your particular case of a science case. This is also the time where if you wanna disable or change some of the detector effects, this is the way where you can do that. By default, detector effects are included. So these are IPC effects, the interpixel capacitance effects, and charge diffusion effects. So basically, what we're trying to accomplish here is to make sure that we add some of the physics of the detectors. Remember, that's outside the scope of the optical path of WebbPSF. We are adding the detector part of it on top of the WebbPSF simulations, optical simulations. The IPCFX are based on either ground or in-flight information based on calibration programs. So this is how the charges on a particular pixel spread to the other neighboring pixels, and those are related or added via a set of kernels, typically a 3x3 kernel that we can add into the simulations. Like I say, these IPCFX are based on test or in-flight observations. These are not included for FGS and NearSpec yet, but we're working on that to include those effects on FGS and NearSpec. But we also have a charge diffusion effect. I don't know if you are already an experienced user of WebbPSF and you're trying to use WebbPSF soon after we launch, you would have noticed that typically the simulated PSF were more compact than the ones that we observe in flight. So you could have thought that maybe you sort of like have almost like a jitter effect, like they look a little bit broader in flight than what we're simulating. And these have nothing to do with jitter because we know the telescope is extremely stable. It's like 7 times or more stable in terms of jitter than the requirements. So this is what we call this charge diffusion, and we are adding that in WebbPSF in a very using a 2D Gaussian. So this is a proxy of detector effects. Now I'm explaining all this just for the sake of telling you the takeaway from this is that detector effects, IPC, and charge diffusion are included by default in the WebbPSF simulation into the extensions that have the geometric distortions. And by default, you'll have those. And the charge diffusion one is something that you can tweak based on your observations. So the values that we have there, we are using a proxy, we're using a 2D Gaussian for the charge diffusion. These are values that are by default in WebbPSF based on observations that we have. So basically we use observation and we're trying to find what are the best values that match the observations. But it is a single value and this changes depending on the filter that you have. So I can see that for some filters, you may want to tweak a little bit that. And the way to do that is you have this dictionary that is called charge diffusion sigma. If you want to remove the charge diffusion from your observations, you just simply set that to 0. Otherwise, you can just change that value to best match your observations. Or if you don't do anything, like in this case, it's just grabbing the value that you have there by default. But like I say, those values are optimized for a particular filter on your instrument. So these are the cases where once you set up this and you're trying to match your observation, this is the case where you may want to tweak a little bit your charge diffusion to best match your observation. In this case, we did a very basic setup, and now this is the case when we can load the optical performance of the telescope at a particular time. What time? Well, the time of your observation. If you know exactly when your observation was taken, you can set that time here, and you can load an OPD that is going to tell you what was the optical performance of the telescope at that time. You have the description here in more detail, but it's basically what we are measuring, the phase map, the optical performance of the telescope that we're measuring at our calibration point, which is a very particular point on A3, on NIRCam A3. And then what happens behind the scenes of WebbPSF is that it's taking that point on NIRCam, it is removing the NIRCam contribution on that particular point. So basically, the wavefront error of the instrument itself on that particular point. So we have the OTE optical performance at that particular point. And then what it does is translate that calibration point to match the point that you're asking the simulation to happen. In this case, the calibration point is in A3, but we really want to know the optical performance of the telescope in B2 in that particular position that I set up. All this is happening behind the scenes of WebbPSF. So the bottom line here is that we take the optical performance of the telescope, we remove the contribution of the instrument, then we move that to the location and the instrument that we want, and then we get a nice optical performance, the phase map at the particular point where you're doing the simulation. All that is described here on this in Excel. So I won't go into much details over there. But I keep talking about the OPDs. I'm just going to show you this quickly. What's inside this OPD? Likely you won't need to deal with any of this information, but I'm sure that if you're curious and you are going to download some of these OPDs, you're going to see that it has many extensions inside. All those extensions are described here, so I won't go into all the details, but it's basically showing you what is the shape of the predicted PSF, what is the pupil mass, so the phase maps that you are observed, what is the phase map if you decide to apply corrections, what are the weak lens images that we observe, and what are the weak lens images that we are simulating, that we're simulating during the process of phase retrieval. And then we can split the phase map into its low frequency or the high frequency. So basically the things that we can control, and by control meaning the things that we can correct with the mirrors, and the high frequency noise on the phase map of things that we cannot correct directly. But all that information is here on the OPDs, and you have some descriptions here. So if you are curious, just read the description. And of course, you can always ask questions. Now, it is not completely irrelevant, some of this information, because you'll see that we have the weak lens images here. There are some imaging modes, especially when you have bright targets and when you have time series observations that do use weak lenses to calculate the images. So weak lenses is not necessarily a sensing only observing mode, but now calibration mode, but now people can use it for some of these very specific cases. Bear in mind. Yeah. Now that basically what I did so far, it was set up a very simple set of observation with the Inflight OPD. We have positions. We know how to set up our detector effects, etc. Then we can just, after all that, we can just calculate the PSF. In this case, I'm just basically calculating the PSF with all the default parameters. And I can display that with a convenient function, WebbPSF display PSF, and it's going to give me a nice view of that PSF. So this is a very simple set of observations just to set up and including the OPD.